Hi there, welcome back. Last time we were talking about doing double integration over regions that were rectangles. And now we'd like to maybe talk about what happens if we have a region that is not a rectangle. Some sort of region that's bounded by functions, or a region that is circular, or some other shape. Does it make sense to take a double integral over that region? So we're asking that question because when we defined double integration, we used this Riemann sum that took our rectangle and broke it down into a whole bunch of smaller rectangles. So how can we justify to ourselves that it makes sense to take an integral, find maybe the volume above a non-rectangular region of a function? Well, here's how we can do that. And it might feel a little bit like cheating, but let's set this up in such a way that an integral over a non-rectangular region actually becomes an integral over a rectangular region. And then we can say we're all good. All right, here's what we're going to do. We are going to say we have our region D, and we're going to fit it inside a rectangle. Okay, so what we've been talking about is having a surface over this region that's defined by z is equal to f of xy. And so we're trying to find this volume under the surface but above our region. What we'll do is we'll take this function that's defined on our domain D and extend it to be defined over the whole rectangle by saying the function is going to be equal to f of xy when we're on D, but then it's going to be equal to 0 outside of D. So in essence, what we've done is we've said, hey, we now have a function that's defined everywhere on this rectangle. When it's in D, it's equal to that other function that we cared about. When it is outside, then our function is equal to 0. And so if we add up all the volume under this function that's 0 everywhere else, that's going to give us 0. And then in the end, doing this integration over d of little f of xy is going to be equal to the same as the integral over the whole rectangle of, I forgot my dA, f of xy, capital F of xy dA. Because what we're doing is we've now made it so the volume under our surface above D is the same as the volume under this more general function that is over the whole rectangle. So we've extended our function, so it's defined over a whole rectangle. We know that integration works on a rectangle, so integration will now work on any region. Good news. All right, so now that we're comfortable with the fact that we can do integration, let's talk about how we do integration. So what the key idea is that it depends on the shape of the domain over which we're going to integrate. So let's talk about the nice way that this could look. The nice way that this could look is that we have a function. So remember, we're in 3 dimensions here. And so it's really helpful to have 2 pictures in mind. First picture is the picture of the domain, which is in the xy plane. And the second picture is of that thing that we're integrating, which is we have some surface and the domain is lying down here. Okay, and so we're saying that here is our domain. And so one type of domain that we can integrate over is a domain where we've got some upper function, g2 of x. We've got some lower function, g1 of x. And we have some bounds here, x equals a, x equals b. And the region is defined to be everything that is between the upper function and the lower function, and within this range x equals a to x equals b. Now sometimes you have to figure out what a and b are, because that might be places where the functions intersect, or it might be something else happening. But in this setup, right, so what this is looking like, here's our x equals a, this is our x equals b, and then we have our g2 of x, and we have our g1 of x. This is our same domain down here. Then the way that we're going to find the volume under the surface above our domain is going to be in this way. So whenever you have a region that looks like this, I like to draw a vertical line here. And this vertical line reminds me that I have a lower function and I have an upper function. And what we're going to do is we're going to do a lot of slicing. So we are in doing double integrals, in doing triple integrals, in doing our polar and cylindrical and spherical integration. I find it very helpful to draw some slices in here to help us remind ourselves what we're doing. So what we're going to do is we're going to first set up an integral with respect to y, and that integral with respect to y is going to be nested inside an integral with respect to x. So you can see here we're slicing with respect to x. The first slices are with respect to x, and for any particular x, what we have is we're going to integrate from the lower bound to the upper bound of this vertical slice. So this outer function is telling us that we are slicing the region with respect to x. And then, so we've got this slice here, and we're basically taking what is the contribution of this integration from this slice of the region. And so we then integrate where y, instead of going like when we were doing the rectangles, right? When we had the rectangles, we had maybe x goes from a to b, and then y goes from c to d. But now the lower bound is not from c to d, it depends on what x is. So we get this really new and different way of thinking about the functions of these bounds of integration, where now the bounds of integrations are functions themselves. We're seeing that when, no matter what x is, we have a different value of y that depends on what x is. So given x, this is g1 of x, that's the lower bound. This is g2 of x, that's the upper bound. All right, so that's what happens if our region is oriented in such a way that every slice that we take, no matter what x we are, we always have this as the upper bound, g2, and this as the lower bound, g1 of x. This is going to be called a type 1 region. They just gave them these names. This is type 1, the next one will be type 2. But this is just saying we need to do vertical slices, slicing with respect to x. So you can imagine that the next option is to slice with respect to y. So if we're in the situation instead where, all right, remember we have two pictures here. We have our domain picture where we have x and y, and then we have our three-dimensional picture where we have x, y, and z. And so we've got this surface, but maybe now our domain looks better like, oh, we've got our two functions like this, where we integrate, and the slices make more sense if we're taking slices with respect to y. And so we see where we start chopping, this is at y equals c, and then we stop chopping at y equals d. Let me erase a tiny bit. So we have this region right here. This is our region D. Right, what does that look like down here? That looks like, all right, this is y is equal to c, this is y equals d. And so this is a region that looks like this. And in this case, we have a lower function, which you could kind of consider a left function, but I kind of like to think of it still as a lower and an upper function, where we're saying on the scale of x, this is a higher value of x, and this is a lower value of x. So if we have this region here where any horizontal slice looks like it goes from this lower function up to this higher function, no matter what y is, then now we're slicing with respect to y. Oops, my integrals, my order here, this should be dx, this should be dy. So we're slicing with respect to y. Then what our picture then looks like, right? So the higher x is up here, the lower x is down here, and our slices are being taken in this direction now with respect to y. Then the double integral over this domain D is going to be equal to this integral. First we integrate with respect to x, where the lower bound is h1 of y and the upper bound is h2 of y, and then we integrate with respect to y, where y goes from c to d. So we first look at the region that we have to integrate over. If the region looks like it's better defined in terms of x with vertical slices, then we would have this type 1 integral. If instead the slices look like they're better horizontal in the domain, then what we'll do is we will use this type 2 integral, where we set up our integral from where we start slicing to where we stop slicing, and then we look at what the upper bound and lower bound are for each of those slices. And so we look at the domain. If the domain is easier in one way than another, then we'll set up our integral that way. If you have a region that maybe looks like you could slice it either vertically or horizontally, then we should look at the function and figure out which way it's easier to integrate the function, just like we did in the last video where we said, oh, it's really a lot easier to do this integral with respect to y instead of with respect to x. All right, so let's stop here. In the next video, we'll do some examples. All right, see you shortly.